In this episode, we're going to explore feature transformations, which are changes you apply to raw values so that the data becomes easier for a model to learn from without changing the underlying meaning. Beginners sometimes hear about transformations and assume they are a way to manipulate the data into looking better, but safe transformations are really about aligning the numeric shape of the data with how learning algorithms behave. Many real-world features are skewed, heavy-tailed, or measured on wildly different scales, and those shapes can cause models to focus on the wrong patterns or to train unstably. Normalization and standardization are common scaling transformations that make magnitudes comparable, while log transforms and Box-Cox transforms reshape distributions to reduce skew and tame extreme values. The word safely matters because transformations can accidentally introduce leakage, distort interpretation, or create values that break assumptions if applied blindly. The goal is to help you understand what each transformation does, when it helps, and how to apply it in a way that keeps the model honest and the results trustworthy. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good first step is to recognize that transformations are not one-size-fits-all, because different features carry different meanings and different constraints. Some features are naturally bounded, like percentages, and forcing them through aggressive transforms can create unnecessary complexity. Some features represent counts, like number of logins, and they often have many small values with a few huge values, which makes them prime candidates for transforms that compress the range. Some features represent money or time durations, and those often behave multiplicatively, meaning ratios matter more than absolute differences, which suggests log-style thinking. Before applying any transformation, you should ask what the feature represents, what its valid range is, and what kinds of differences are meaningful in context. This meaning-first step prevents you from applying a mathematically convenient transform that produces values that are technically valid but conceptually confusing. Transformations are most helpful when they respect the real-world semantics of the measurement. Normalization is a transformation that typically rescales values into a fixed range, often 0 to 1, so that features with different raw magnitudes become comparable. The intuitive idea is that you measure each value relative to the minimum and maximum observed in your training data, turning the smallest into 0, the largest into 1, and everything else into a proportion in between. This can be useful for algorithms that are sensitive to the scale of inputs, because it prevents a large-scale feature from dominating the learning process just because its numbers are bigger. Normalization can also make certain distances and similarities more meaningful when you combine features, since all features contribute within the same numeric range. The safety concern is that minimum and maximum values can be influenced by outliers, meaning one extreme value can stretch the range and compress most observations into a narrow band. Another safety concern is that future data might contain values outside the original range, which then produces normalized values less than 0 or greater than 1, so you need to understand whether that behavior is acceptable for your use case. Standardization is another common scaling transform, and it typically centers a feature around 0 and scales it based on its spread, often described in terms of standard deviations from the mean. Instead of forcing values into a fixed range, standardization produces values that indicate how far above or below typical a value is relative to the variability of the feature. This can make learning more stable because many optimization methods behave better when inputs are roughly centered and similarly scaled. It also helps interpret linear model coefficients because features are on comparable scales, which makes coefficient magnitudes more meaningful. A key safety point is that standardization assumes the mean and spread are sensible summaries, and if the distribution is extremely skewed or heavy-tailed, the mean and standard deviation can be pulled by outliers. In that case, standardized values can still be dominated by a few extremes, and you might need a transformation that reshapes the distribution first. So standardization is often a good default, but it works best when the underlying distribution is not wildly irregular. A major safety rule for both normalization and standardization is that you must learn the transformation parameters using only training data, then apply the same parameters to validation and test data. If you compute the mean, standard deviation, minimum, or maximum using the full dataset, you are letting information from the evaluation data influence the transformation. This can make performance look slightly better than it should, and in some cases it can create more serious leakage, especially when the distribution of values shifts over time. The safest mental model is that transformations are part of the model, not a separate step, because they define how raw inputs become model inputs. That means they must be fit in the same disciplined way you fit model parameters, using only information that would be available at training time. When you treat transformations as part of the pipeline, you avoid the common beginner mistake of pre-processing everything first and then splitting, which silently breaks the rules of honest evaluation. Log transforms are among the most useful distribution shaping transforms, especially for right-skewed features that have a long tail of large values. The basic idea is that a log compresses large values more than small values, reducing the dominance of extremes and making the distribution more balanced. Log transforms often turn multiplicative differences into additive differences, meaning a change from 10 to 100 becomes similar to a change from 100 to 1000, because both are tenfold increases. This is a good match for many real-world patterns where relative changes matter more than absolute changes, such as growth, decay, and rate-based behavior. The biggest safety issue is that logs are not defined for zero or negative values in the usual sense, so you need a strategy for handling zeros, such as using a shifted log where you add a small constant. Another safety issue is interpretation. Once you transform, model outputs and relationships are expressed in log space, which changes how you explain effects back in the original units. The transform is still valid, but you must remember what scale you are thinking in. Box-Cox transforms are a family of power transforms that can be thought of as a general framework that includes log-like behavior as a special case. The idea is to find a power transformation that makes the distribution closer to symmetric and reduces skew, often making modeling assumptions more reasonable. Instead of choosing log by default, Box-Cox selects a power parameter that best stabilizes variance and shapes the distribution toward a more bell-like form. For a beginner, the practical intuition is that Box-Cox is like a dial that controls how aggressively you compress large values and how you reshape the feature. When the dial setting is near 0, the transform behaves like a log transform, and when it is near 1, it behaves closer to leaving the data unchanged. The main constraint is that Box-Cox typically requires strictly positive values, so you need to shift the data if zeros or negatives exist, and that shift must be done thoughtfully. The safety lesson is that Box-Cox can be powerful, but it adds complexity, so you use it when you have a clear skew or variance problem that simpler transforms do not solve. Transformations also affect outliers, and beginners should learn the difference between handling outliers by transforming versus handling outliers by removing or capping. A log or Box-Cox transform can reduce the impact of extreme values by compressing them, which often preserves information while making the learning process less sensitive. Removing outliers can throw away rare but meaningful cases, and capping outliers can flatten genuine extremes into a boundary value, which can hide important risk signals. Transforming can be a middle path, but it is not always enough if the outliers are errors rather than real values. This is why safe transformation involves first deciding whether extreme values are plausible in the real world, then deciding whether you want the model to be sensitive to them or robust against them. A feature representing response time might need robustness because rare outages could dominate, while a feature representing fraud amounts might need sensitivity because rare large values could be critical. The right choice depends on the role the feature plays in the problem. Another key part of safe transformation is thinking about how transformations interact with the model's assumptions and with the metrics you care about. If you transform the target variable, not just the features, you can change what the model is effectively optimizing, because errors in transformed space correspond to different kinds of errors in the original space. A model trained on log transform targets tends to focus on relative error, which can be desirable when proportional accuracy matters. But if your real-world decision needs absolute accuracy, you must be careful about interpreting and evaluating predictions back on the original scale. Even for feature transforms, the model might learn relationships that are linear in transformed space but nonlinear in original space, which can be perfectly fine as long as you interpret it correctly. The point is not to avoid transformations. It is to align them with the meaning of error and the meaning of change in your domain. Safety in transformation is about preserving the question you are trying to answer. A practical beginner habit is to treat transformation selection as part of your EDA loop, meaning you look at a feature's distribution, decide what problem you are solving, apply a candidate transform conceptually, and then recheck what the shape would look like after. If the feature is extremely right-skewed, a log-like transform is often a reasonable first try because it compresses extremes and spreads out small values. If the feature has a wide range but is not extremely skewed, standardization might be enough to stabilize learning. If the feature has a bounded range, normalization might help if scale matters for the algorithm, but it will not fix skew if the distribution clumps at one end. If you have multiple features with different problems, you may use different transforms for different features rather than applying one global rule. This is what it means to transform safely. You match the transform to the feature's shape and meaning instead of doing everything automatically. By the end of this topic, you should see normalization, standardization, log transforms, and Box-Cox transforms as tools for making learning more stable and more meaningful, not as tricks for making data look nicer. Normalization rescales values into a fixed range and helps when magnitude differences would otherwise distort learning, while standardization centers and scales values to make them comparable and to support stable optimization. Log transforms reshape right-skewed distributions by compressing large values and emphasizing relative change, but they require careful handling of zeros and interpretation in the original units. Box-Cox transforms generalize log-like behavior and can be tuned to reduce skew and stabilize variance, but they require positive data and add complexity that should be justified by a real need. Safe transformation means fitting transform parameters on training data only, respecting valid ranges and edge cases, and keeping the transform values tied to the real-world meaning of the original measurement. When you adopt that mindset, transformations become a reliable part of your modeling pipeline rather than a source of hidden mistakes.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.